Good afternoon and welcome back to Dr. Logic Awkwardly Does Logic. We've got our truth and membership lemma, and now I'm going to give you in this video a quick, short and sweet, and very easy to prove corollary. This is the last step of what we need before we can actually then take these canonical models that we have been constructing, it feels like forever, and actually using them to show how we have a general method for proving the completeness of a very large and useful class of modal systems. So without further ado, let me get up the whiteboard, back to the classic one, because that's the one that we need. And what is the corollary? Short, simple, easy to state. The corollary says that if we have the canonical model for some particular system S, and phi is valid on the model, that it is true in every world, this is the case if and only if phi is, in fact, a theorem of the system. So this is an if and only if claim. This means that we need to prove both directions. I'm going to start by proving left to right. So if phi is a theorem of S, so that's what we are assuming, then by how we defined maximal S-consistent sets, we know that every maximal S-consistent set contains phi. So every maximal S-consistent set lambda contains phi. Now, by the truth and membership lemma that we've just proven, and I'm just going to call it T and M, phi is the member of one of these maximal S-consistent sets if and only if lambda makes phi true on this model. But this holds for every lambda because it doesn't matter which one we have said. We said here, every maximal S-consistent set contains phi. So it follows from this, since it is true of every lambda, then phi is going to be true at every world in the canonical model. That's one direction. The other direction, so going from left to right, we'll actually, as we often do, prove this contrapositively. So suppose that we've got some formula phi, which is not a theorem of our system, so we can't prove it. Then we know that the set containing not phi is S-consistent, and therefore, by Lindenbaum's lemma, included in some maximal consistent set. So there is a maximal S-consistent set containing not phi. Let's call it gamma, just so that we don't get confused with the lambdas in the other one. So we've got this maximal S-consistent set gamma. Not phi is a member of it. So let's write this out. Not phi is a member of gamma. Again, by truth and membership, this means that gamma makes not phi true. So there is a world in the canonical model that makes phi false. That means that phi is not going to be valid on the canonical model, because we can find a falsifying thing. So there we go. This is exactly what we need to show that there is this deep correlation between validity in the canonical model and provability in the system. So all and only the theorems are valid on the canonical model. And by now, I hope you're thinking, oh, I see why this is useful. I think I see why this is such a powerful result. Because what are we trying to do? We are trying to show that every non-theorem has a falsifying model. However, it's not just any model. It has to be a model for the logic. We've constructed this canonical model out of particular systems. But what we need to show next, and this is the task of proving that a system is canonical by proving the canonicity of its canonical model, is to show that the frame that underlies this model that we've constructed is in fact a frame for the logic in question. That will be what we will move on to next. We will show it for a number of systems. It will be trivial in the case of K. It will be not quite so trivial in some of the other cases. And then after we've gone through a bunch of examples to show that we do have canonical logics, we will also show an example of something that isn't. That is a logic where the canonical model, the frame of that model, is not a frame for the logic in question. Super cool stuff, lots of fun. Hope you will join me then. Until then, take care. Cheers.